Learning objectives. At the end of this topic, you will be able to describe trigonometric ratios for some special angles, learn trigonometric ratios of complementary angles, understand trigonometric identities, evaluate problems based on trigonometric identities. Introduction. Trigonometric ratios of specific angles. In triangle ABC, right-angled at B, if one angle is 45 degrees, then the other angle is also 45 degrees. That is, angle A equal to angle C is equal to 45 degrees. Hence, BC is equal to AB. Then, by Pythagoras theorem, let's now calculate the trigonometric ratios of 30 degree and 60 degree. Consider an equilateral triangle ABC. Since each angle in an equilateral triangle is 60 degrees, therefore, angle A is equal to angle B is equal to angle C is equal to 60 degrees. Draw the perpendicular AD from A to the side BC. Now observe that triangle ABD is a right triangle, right-angled at D, with angle BAD equal to 30 degrees and angle ABD equal to 60 degrees. As you know, for finding the trigonometric ratios, we need to know the lengths of the sides of the triangle. So let us suppose that AB is equal to 2 small a. Now let's calculate trigonometric ratios of 0 degree and 90 degree. Let us see what happens to the trigonometric ratios of angle A. If it is made smaller and smaller in the right triangle ABC till it becomes 0. As angle A gets smaller and smaller, the length of the side BC decreases. The point C gets closer to point B, and finally when angle A becomes very close to 0 degree, AC becomes almost the same as AB. When angle A is very close to 0 degree, BC gets very close to 0, and so the value of sin A is equal to BB by AC is very close to 0. When angle A is very close to 0 degree, AC is nearly the same as AB, and so the value of cos A equal to AB by AC is very close to 1. This helps us to see how we can define the values of sin A and cos A when A is equal to 0 degrees. We define sin 0 degree equal to 0 and cos 0 degree equal to 1. Using these we have, as angle A gets larger and larger, angle C gets smaller and smaller. Therefore, as in the case above, the length of the side AB goes on decreasing. The point A gets closer to point B. Finally, when angle A is very close to 90 degree, angle C becomes very close to 0 degree, and the side AC almost coincides with side BC. Angle A is very close to 90 degrees. Side AC is nearly the same as side BC, and so sin A is very close to 1. Also, when angle A is very close to 90 degrees. When angle C is very close to 0 degree, and the side AB is nearly 0, so cos A is very close to 0. So we define sin 90 degree equal to 1 and cos 90 degree equal to 0. Trigonometric ratios of specific angles. Table shown gives the values of all the trigonometric ratios of 0 degree, 30 degrees, 45 degrees, 60 degrees, and 90 degrees for ready reference. From the table, we can observe that as angle A increases from 0 degree to 90 degrees, sin A increases from 0 to 1, and cos A decreases from 1 to 0. Let us illustrate the use of the values in the table seen earlier through some examples. What is the value of 2 sin 30 degree plus 3 cos 60 degree minus 3 tan 45 degree? Let's move to another example. What is the value of 3 of cos 30 degree square plus 2 of sin 30 degree square? Trigonometric ratios for complementary angle. We know that two angles are said to be complementary if their sum equals 90 degrees. In triangle ABC, right-angled at B, let's note down complementary angles. Since angle A plus angle C is equal to 90 degrees, they form such a pair. We have Now let's write the trigonometric ratios for angle C is equal to 90 degrees minus angle A. Now comparing the ratios in 1 and 2, observe that hence we can conclude with some findings. Note, tan 0 degree equal to 0 is equal to cot 90 degrees, secant 0 degree equal to 1 equal to cosecant 90 degrees, and secant 90 degrees, cosecant 0 degree, tan 90 degrees, and cot 0 degrees are not defined. Let us solve some examples relating to trigonometric ratios for complementary angles. Evaluate sin 35 degree, sin 55 degree, minus cos 35 degree, cos 55 degree. Let us move to another example. If secant 5 theta is equal to cosecant of theta minus 36 degree, where phi theta is an acute angle, find the value of theta. Let's move to another example. Using trigonometric ratios of complementary angles, prove that tan 1 degree, tan 2 degree, tan 3 degree, and so on up to tan 89 degree is equal to 1. We know that an equation is called an identity when it is true for all values of the variables involved. Similarly, an equation involving trigonometric ratios of an angle is called a trigonometric identity if it is true for all values of the angles involved. We will prove one trigonometric identity and use it further to prove other useful trigonometric identities. In triangle ABC, right-angled at B in the figure, we have Let us now divide 1 by AB square. We get Let us now divide 1 by BC square. We get Using these identities, we can express each trigonometric ratio in terms of other trigonometric ratios. That is, if any one of the ratios is known, we can determine the values of the other trigonometric ratios. Let's solve some examples to have better understanding. Tan x sin x plus cos x is equal to secant x. Let's move to another example. Sin x minus sin x cos square x is equal to sin cube x. Summary. Let's summarize the topic. The value of sin A or cos A never exceeds 1, whereas the value of secant A or cosecant A is always greater than or equal to 1. Sin 90 degree minus A is equal to cos A. Cos of 90 degree minus A is equal to sin A. Tan of 90 degree minus A is equal to cot A. Cot of 90 degree minus A is equal to tan A. Secant of 90 degree minus A is equal to cosecant A. Cosecant of 90 degree minus A is equal to secant A. Sin square A plus cos square A is equal to 1. Secant square A minus tan square A is equal to 1 for 0 degree less than equal to A less than 90 degree. Cosecant square A is equal to 1 plus cot square A for 0 degree less than A less than equal to 90 degree.